Hello and welcome to my Computational LAB3 presentation where the Schrödinger equation is considered in three different scenarios. In part 1, Orca was used to calculate the potential energy curves for the dissociation of HBr, HCl and HF with different internuclear distance between the ranges of 0.4 and 3 angstrom. This allowed equilibrium distance and dissociation energy of each molecule to be determined. For this calculation, the Hartree-Fock method was used as it follows the three approximations of Born-Oppenheimer, orbital, and mean field. Furthermore, we used a minimal basis set, as you can see is the STO3G. To find equilibrium distance, we need the assistance of restricted and unrestricted calculations as they narrow down possible distant range. With restricted HF, a single determinant of electron orbitals with a set of 4 quantum numbers are assigned. It is assumed that all functions with the same principal and angular quantum numbers but different magnetic spin functions according to SNL operators. This results in alpha and beta spin orbitals being idempotent. With unrestricted HF, the spin orbitals are not idempotent and the previous assumption is dropped, causing variation of electron orbitals with different quantum numbers. This causes alpha and beta orbitals to be calculated separately. With this in place, the equilibrium distance in between these two values are shown in Table 1. The Mulligan charges refer to the overlap between atomic orbitals of different sizes. This leads to charge displacement at the midpoint of equilibrium distance. Therefore, the electric dipole moment of molecules is affected. So in terms of the data, at 3 angstrom, it was found that fluorine had a smallest charge of minus 0.058, whilst chlorine had the greatest charge of minus 0.254. Using the data from the table, the similar potential energy curves of HBr and HCl was produced as shown in Figure 1 and Figure 2 respectively. As seen, there's a restrictive part, which is this part seen here, and this one here, and an unrestrictive part, which is here and here. The point where these differ is the point of dissociation of the molecule, and in both figures, this is seen at roughly 1.6 angstrom. This point can then be used to find the dissociation energy by subtracting this value from the energy at full separation, which is at this point here. As a result, HBr has a dissociation energy of 7.73 eV, whilst HCl has 8.61 eV. This correlated with their respective bond length, as HBr has a longer bond compared to HCl, resulting in less energy needed to dissociate. The electronic structure of 4 diatomic molecules is considered, where the respective molecular orbitals are observed based on their energy and shape. Furthermore, bond distances are considered along with how changes in charge affects this. The molecular orbitals for diatomic carbon, nitrogen, oxygen and fluorine are observed with their respective s orbitals and p orbitals shown. As seen, whilst both carbon and nitrogen have 5 orbitals, only 2 have the same shape, which is seen in pi u in this orbital here, and sigma g for the 2p orbital, which is these two, suggesting that there is different overlap of orbitals. In comparison, however, fluorine and oxygen have 6 different molecular orbitals, and out of those 6, only one is different, which is the sigma g for the 2s, which is seen here, whilst the rest share the same shaped orbital, suggesting there's similar overlap. In Figure 3, you can see the molecular orbital diagrams for the 4 diatomic molecules. And using Orca, the appropriate energy levels for each orbital was assigned, as you can see. The data collected from the calculation suggests that the energy obtained from the molecules agree with the molecular orbital diagrams, and as you can see, they have all been assigned. The trends seen in the energies correspond well with the positions of the orbitals, as all are increasing towards 0 eV, as you can see, and have the same energies for degenerate orbitals. As you can see in carbon, these two degenerate orbitals of pi u both have the same energy levels of minus 10.17. Furthermore, in relation to the electronegativity of the molecules, the energy from carbon to fluorine is becoming more negative, which is clearly seen with the sigma g orbitals, as carbon has minus 26.49 eV, whilst fluorine has minus 55.87. We can now consider how and why that bond length changes. In Table 2, the bond distances of the four diatomic molecules are shown. As seen, F2 has the greatest bond length of 1.315 angstrom, whilst N2 has the shortest with a length of 1.134 angstrom. This is due to the bond orders of the molecules. F2 has a single bond and therefore a bond order of 1, causing it to have the greatest bond length, whilst carbon and oxygen both contain a double bond, which explains why their bond lengths are quite similar, as they both have a bond order of 2. However, N2 has a triple bond, causing it to have the shortest length due to the bond order being 3. Now, to see the effects of charge on bond distance, dioxygen 2- and 2+ were considered along with their molecular orbital diagrams. The same method was used to find the molecular orbitals and bond lengths of these two. However, instead of having a charge of 1 and a multiplicity of 3 with O2, the charge was changed to plus or 2- and a multiplicity was 1. As you can see, the charge is here and here, along with the multiplicity being here and here. From this, the bond length of dioxygen 2- and 2+ was calculated to be 1.46 and 1.15 respectively. Compared to neutral dioxygen, the bond length increases with a negative charge, but decreases with a positive charge. As you can see here with the O2-, the neutral dioxygen is 1.217, but this one has a bond length of 1.46, showing it increasing. On the other hand, this one is 1.145, showing it decreasing from this value. Finally, in part 3, the radial function and hydrogenic orbitals of different s and p orbitals were graphically represented, and therefore the favorability of electrons were determined. Firstly, the radial functions of 2s and 2p orbitals were defined appropriately, as you can see here, where the atomic number, otherwise known as Z, and the Bohr radius, or A, is assumed to be 1 as it is in the hydrogen orbital. This is then plotted, which is seen in figure 4, as you can see, and as seen, the magenta line has a single peak here, whilst the dark blue line represents 2s, and it also indicates a radial node as it goes below the radial function. From this, the radial distribution factor, otherwise known as RDF, was then plotted to indicate the probability of finding an electron between the equilibrium distance and beyond within a given angular and radial function of the surface of a sphere, which is seen in figure 5 and 6. And the equation to calculate RDF is seen here. As seen in figure 5, you can see there are two peaks, which might be due to the presence of the radial node, as this represents the 2s orbital. However, when comparing the two probabilities between figure 5 and 6, there's a greater RDF in figure 6. As you can see, it goes all the way up to 80 in this one, whilst this one only goes up to 2.5, which suggests that figure 6 has a greater density probability in the 2p orbital, and therefore that's more probable as to where you'll find an electron. Lastly, the hydrogenic orbital of 1s was defined, as you can see here, and then plotted as shown in figure 7. As seen, there's a dramatic decrease until it plateaus at 5 angstrom, as you can see here. When squaring this hydrogenic orbital, as shown in figure 8, as you can see, it shows the coordinates of the electrons present in the orbital based on its quantum numbers. The graph suggests that the electron is within the orbital closest to the nucleus due to there being the greatest electron density, as the bore radius is only going up to around 1, showing it is the most closest to the nucleus. Thank you for listening.